de Broglie wave equation. This equation actually equates the views of two sets of scientists. First were the classical mechanists who believed that an electron is like a particle, or it acts like a wave. That is, either it acts like a particle or it acts like a wave. The second set of scientists, which we call the quantum mechanists, they said that the electron behaves as a particle as well as a wave. So, if electron behaves like a particle, then its energy can be said to be E is equal to mc square, where E is the energy, m is the mass of electron, and c is the velocity of light. Right? Now, if it behaves like a wave, then E is equal to h mu, where again E is the energy, h is Planck's constant, and mu is the frequency of the electron wave. So if we equate both the equations, E is equal to h mu and E is equal to mc square, then we'll say h mu is equal to mc square. Now, mu is equal to c upon lambda, where lambda is the wavelength if the electron behaves like a wave, and c of course the velocity of light. So we can write h mu is equal to hc upon lambda. So we can write here mc square is equal to h c upon lambda. Now this and this will cancel out. So we can say mc is equal to h upon lambda. Or you can say is equal to h upon mc. Now mass into velocity is equal to momentum, which we designate by P. So we can say lambda is equal to h upon P, and this is de Broglie's wave equation. Planck's quantum theory. Well, Max Planck, he gave this theory, and he said light falls in the form of bundles, or you can say packets. That is, you have one bundle of light falling, you have another bundle of light falling, or you have another packet of light falling. And he called this bundle or packet as quanta. Quanta is actually plural and singular is quantum. So he said light falls in the form of packets or which he called as quantum. Now these quantum, they consist of millions of particles of light which are called photons. He also said that the energy of this quantum is proportional to the frequency which is called mu. This is the frequency. And you know it pretty well that if we remove the proportionality sign, we have to put a constant. So he said E is equal to h mu, where h is Planck's constant. And the value of Planck's constant h is 6.626 into 10 to the power minus 34 joules second. This is the value of Planck's constant. The velocity of an electron is 1.6 into 10 to the power 6 meters per second. Calculate the de Broglie wavelength. The solution is lambda is equal to h upon mv, or lambda is equal to 6.62 into 10 to the power minus 34 upon mass of electron is 9.1 into 10 to the power minus 31 kilogram into 1.6 into 10 to the power 6. So this comes to 4.55 into 10 to the power minus 10 meters. Planck's quantum theory. Well, Max Planck, he gave this theory, and he said light falls in the form of bundles, or you can say packets. That is, you have one bundle of light falling, you have another bundle of light falling, or you have another packet of light falling. And he called this bundle or packet as quanta. Quanta is actually plural and singular is quantum. So he said light falls in the form of packets, or which he called as quantum. Now these quantum, they consist of millions of particles of light which are called photons. He also said that the energy of this quantum is proportional to the frequency which is called mu. This is the frequency. And you know it pretty well that if we remove the proportionality sign, we have to put a constant. So he said E is equal to h mu, where h is Planck's constant. And the value of Planck's constant H is 6.626 into 10 to the power minus 34 joules second. This is the value of Planck's constant. Photoelectric effect. It was discovered by and explained by Albert Einstein. It says when a light of a particular frequency is incident on the surface of a metal, electrons are knocked off, are emitted. And this phenomenon is called photoelectric effect. Now supposing you have, let's say, a metal, and for example you have sodium as a metal, and the electronic configuration of sodium is 1, so 2 8 and 1. Now the electronic configuration of sodium is 2 8 1. That means every atom of sodium has 1 electron in the outermost shell. If this electron acquires sufficient energy, it will come out of the shell. It will come out of the atom. So what happens? Let's say you have the source of electrons, which is the metal. Let's say it is sodium. And light is emitted, or light is focused on it, light is incident on it. Now, to remove the electron, light must have a certain minimum frequency. Which is called threshold frequency. And corresponding to threshold frequency, we have threshold energy. Right? So light of certain minimum threshold energy or threshold frequency should be incident on the metal. Once light of certain minimum frequency, which we call the threshold frequency, it is incident on the metal, the electron comes out of it, out of the metal. Now the point here is, let's say the light required or the minimum energy required for the coming out of electron, let's just suppose is 20 kilojoules. Okay. And the light which is incident on it has energy equal to 40 kilojoules. Now out of this 40 kilojoules, 20 kilojoules will be required to knock off the electron from the atom, and the rest 20 kilojoules, once the electron comes out, it will not be stationary over there, it will start running. Because if it has energy, it will start moving, it will start running. Or rather we can say the rest 20 kilojoules is used by electron as kinetic energy. So we can say the total energy which is incident on the electron is E, total energy incident, and the energy required for emitting the electron is called threshold energy. It is E0. And once the electron comes out and it has extra energy, as I said, it shall start moving. And the energy which it uses in moving is half mv square, or kinetic energy. So the total energy can be equated as E is equal to E0 plus kinetic energy. And as E is equal to h mu, or E0 is equal to h mu 0, we can write h mu is equal to h mu 0 plus kinetic energy, or we can also write h mu is equal to h mu 0 plus half mv square. Now here this h mu 0, this is called the work function, or the energy required to knock off the electron. It is called the work function. Let me write it more clearly. We can also write this equation as h mu minus h mu 0 is equal to half mv square, or h into mu minus mu 0 is equal to half mv square. So this is basically the equation for photoelectric effect. Now there are certain points to be remembered. Number 1, for emission of electron, certain minimum energy or certain minimum frequency is required, which is called threshold frequency. No matter howsoever much the intensity of light may be, the intensity of light does not determine the emission of electrons. Only if light of certain minimum frequency, which is mu 0, this is responsible for emission of electrons. Secondly, the intensity of light determines number of electrons emitted. So if you increase the intensity, number of electrons emitted will be more. But if light of certain minimum frequency is incident on it, so once the light of certain minimum frequency is incident on it, then if you increase the intensity, number of electrons emitted will be more. So intensity, or you can say number of electrons emitted is proportional to intensity of light. Okay, so this is basically a photoelectric. Calculate the minimum energy required or the threshold energy required to eject an electron from cesium metal the threshold frequency is 4.6 into 10 to the power 14 second inverse. H is equal to 6.6 into 10 to the power minus 34 joule second. So let's solve this. E0 is equal to h mu 0. So this is equal to 6.626 into 10 to the power minus 34 into 4.6 into 10 to the power 14. So this will be equal to 3.05 into 10 to the power minus 19 joules. The wavelength of the visible spectrum extends from violet (400 nanometers) to red 750 nanometers. Express this wavelength these wavelengths in frequencies. So now we have the solution to this. Mu is equal to c upon lambda, and that is equal to 3 into 10 to the power 8 upon 400 into 10 to the power minus 9. So we can say this is equal to 3 into 10 to the power 15 upon 400. So this is equal to 7.5 into 10 to the power 14 hertz. Next, second part we have mu is equal to c upon lambda. This is equal to 3 into 10 to the power 8 upon 750 into 10 to the power minus 9. So this is equal to 3 into 10 to the power 8, 10 to the power 17 upon 750. So this will be equal to 4 into 10 to the power 14 hertz. Next question, we can take another question here. Yellow light emitted from a sodium lamp has a wavelength of 580 nanometers. Calculate frequency mu and wave number. Now wave number is 1 upon lambda of this light. Solution is, we have to find the wavelength, frequency, sorry. So mu is equal to c upon lambda, that is equal to 3 into 10 to the power 8 upon lambda is 580 into 10 to the power minus 9. So this will be equal to 5.17 into 10 to the power 14 second inverse. Next we have mu bar. This is equal to 1 upon lambda. So this is equal to 1 upon 580 into 10 to the power minus 9. So this will be equal to 1.72 into 10 to the power 14 second inverse. Sorry, meter inverse. Another way of finding the 1 upon lambda is, or mu bar is, mu is equal to c upon lambda. Therefore, mu upon c is equal to 1 upon lambda, and mu upon c is equal to frequency we've calculated as 5.17 into 10 to the power 14 upon 3 into 10 to the power 8. So you'll get the same value, 1.72 into 10 to the power 6 meter inverse.